onto equations of motion. Easiest, by far, way to make a prediction. Mathematical equation. Another way to represent motion is with an equation. We can write position-time equation, formerly known as a position versus time equation, or position as a function of time equation. The equation can be used to tell us where the object is anytime we want, no matter how precise that time. We can also write a velocity-time equation, or velocity versus time equation, or velocity as a function of time equation. The equation can be used to tell us how fast the object is moving at any time. For now, we're only going to worry about position-time equations. We learned previously that we had our average velocity as our displacement over time interval. If velocity stays constant, we can drop the average, because the average is the same number over and over again with itself. So next we're going to rearrange so that the position is on the left by itself. Then we'll expand that delta x, remembering that delta x equals our final minus our initial. Position now minus the initial position, pronounced x naught. That little subscript 0 is x naught. Naught just means happening at the very beginning. It's kind of as if it assumes the starting time is 0. So at the very beginning, that naught, x naught. Likewise, t minus t naught. Solving for the final position, we get this equation. So we just took this and we added the initial plus x naught to the side. So we now have x is the position, the object's position right now, x naught, the position of the object at the beginning of its motion, v, the constant speed of the object, the t, the time right now, and then t naught, the clock time at the beginning of the motion. The equation for final position appears on the equation chart for AP Physics 1. Note that it puts initial position first. Okay, so same equation, it just took initial position and put it up front. And then the velocity has a subscript x, which is just reminding you that the velocity must be horizontal if the horizontal position changes. So if we have motion going horizontally, then our velocity has to be horizontal. We can't calculate horizontal velocity for something doing this. We can do it like this, but that's a little bit trickier and takes a couple more steps, which we'll get to. You can change all of the x's to y's for vertical motion if you want. If you are dealing with one-dimensional motion like this, where it's up and down, then yes, it makes sense to me to change them to y's. And that comes back into the diagonal motion, is you're going to have vertical motion and horizontal motion happening at the same time. So it's useful for organizational purposes to keep your x's and y's separate. If the velocity is constant, the acceleration is 0. So the last term disappears. Listen. This thing right here will probably be 2 or 3 points on your AP exam. If your velocity is constant, the acceleration is 0. And anything having to do with acceleration is 0. Okay, so just keep that in mind. Alright, what's next? Hey, get rid of that. Example. Alright, go ahead and read over that. Let midnight is t equals 0. At 7 a.m., a train leaves the station at 200 miles east of St. Louis and travels west at 200 miles per hour. I gave the answer, sorry. So, here we go. We have negative 50 times t minus 7 plus 200. Okay, so we're using negative 50 because velocity is 50 miles per hour. West. I don't know what I look like. I don't know if that's either west or not. But anyway, so it's going west. So if we assume right to be positive, right is east, so then west must be the opposite, or negative. So it's negative 50. We plug 7 into T naught because the train leaves 7 hours after midnight. So T equals 0 is midnight. And we plug 200 into X naught because the position of the train when the motion started is 200 miles east of the origin. So be careful there, because I can see you reading this and saying, oh, 200 miles east of St. Louis, that must be our final position. No, that's not what the question's saying. And this is what will trip up a lot of students working with physics problems, is not reading the question carefully. Train leaves the station 200 miles east of St. Louis and then travels west at 50 miles per hour. Okay, so be careful of that. And I think if we actually had the rest of the question here, some more context, I believe that'd be a little bit easier. Oh, we did that. We can then take a table and plug in the different times, if we wanted to get the values for x. Now, let's say we gave you that car 1 starts at position x equals 100 meters, going 30 meters per second to the right. Car 2 starts at position x equals 300 meters, going 10 meters per second to the right. When do the cars meet? Where do the cars meet? Suppose you have a car A that starts position x equals 300 meters, going 10 meters per second to the right. Car B starts at position x, 100 meters, going 30 meters per second to the right. Make equations for each car from x equals v times t minus t naught plus x naught. We can say t naught equals 0 because both cars start at the same exact time. Car's A equation becomes that. Car B's equation becomes that. What do you think the next step is? When the cars meet, they have the same position, so we can just set x equals x and solve for the first time. This is such a groundbreaking moment for you. This is so useful because we're taking two completely different equations, finding what's common between them, and setting those two things equal to each other. So we know that x sub a equals 10t plus 300. And x sub b equals 30t plus 100. So that means 30t plus 100 has to equal 10t plus 300 because x equals x. So when you take two things that have something common between them, just set them equal to each other. And we can get the time. Now we can go back, take this time, plug it in either one of these equations and find the exact position. And here's what it looks like. This is an actual simulator. It's not just some random cartoon. One of the main reasons why I chose these PowerPoints is these are these simulations. Very helpful. At least to me, anyway. I don't know about you guys. We're going to do this one next.